So we know hemoglobin is made out of 4 subunits, and we know each subunit can bind an oxygen molecule. For example, we have this oxygen molecule and it binds to this hemoglobin, and that's what hemoglobin does. It binds oxygen molecules. So now that we know this, let's say we have this aqueous solution with these hemoglobin molecules, and let's say we were able to manipulate the partial pressure of oxygen up here. So for example, let's say we have a partial pressure of oxygen of 20 millimeters of mercury. What's going to happen? We know that oxygen is going to dissolve in the aqueous solution, and then it's going to bind hemoglobin molecules. So maybe at this particular partial pressure of oxygen, maybe 30% of the hemoglobin is bound to oxygen. However, now let's say we increase the partial pressure of oxygen. Now let's say we have a partial pressure of oxygen of 35 millimeters of mercury. What's going to happen? We know that oxygen is going to dissolve and it's going to bind hemoglobin molecules. So maybe at 35 millimeters of mercury partial pressure, maybe 65% of the hemoglobin is bound at oxygen. And now let's do another example. Let's say we increase the partial pressure of oxygen to 80 millimeters of mercury. What's going to happen? We know that oxygen is going to dissolve and it's going to bind hemoglobin molecules. So maybe at 80 millimeters of mercury, maybe 90% of the hemoglobin binds oxygen. So this makes sense. As we increase the partial pressure of oxygen, more oxygen is going to dissolve, so therefore more oxygen is going to bind. And we're going to have a higher percentage of the hemoglobin bounded to oxygen. So now we can visualize this with a graph. And again, we can plug in our values. We know this would be represented by this value, because again, 20 millimeters of mercury, partial pressure, 30% is bounded. So again, this represents the partial pressure of hemoglobin, this represents the percentage bound. So we can take any partial pressure of oxygen and see what percentage of the hemoglobin will be bound. And this is what the curve would look like. We would have this sigmoidal shape. But why? Why do we form the sigmoidal shape? Why wouldn't we just form a linear shape? What's with the sigmoidal shape? Well, in biochemistry, whenever you see a sigmoidal shape, which again, it's sigmoidal, it looks like an S, that's how I like to remember it. Whenever you see a sigmoidal shape, you should associate that with cooperativity. So this is a sigmoidal shape because this hemoglobin molecule goes through cooperativity. So what is cooperativity? Well, we know we have these 4 subunits where each combine an oxygen molecule. So when none of the subunits have bound in an oxygen molecule, when they're all empty, they have a very low affinity for oxygen. They all bind oxygen very weakly. However, once an oxygen molecule binds to one of the subunits, then the other subunits increase their affinity for oxygen. They cooperate and they go through a conformational change where now they have a higher affinity for oxygen. Now another oxygen molecule binds. Now these go through another conformational change. Now their affinity for oxygen increases even more. They cooperate, so their affinity for oxygen increases even more. Now another oxygen molecule binds. Now this last subunit has a huge affinity for oxygen. It's cooperating, and this phenomena is referred to as cooperativity, where they work together, where once an oxygen molecule binds, now the other subunits increase their affinity. And that results in the sigmoidal shape. But why? What's the purpose? What's the evolutionary purpose of having cooperativity to create this sigmoidal shape? Well, let's think about what's going on. Let's say this is our lungs. Let's say this is our alveoli in our lungs. We know we're breathing. So if we're breathing that oxygen, we're breathing in that oxygen. So we're going to have a high partial pressure of oxygen. In our alveoli, we're going to have a high partial pressure of oxygen. However, in our respiring tissues and cells, we're going to have a low partial pressure of oxygen because we know our cells are using up oxygen. Our cells use this oxygen as the final electron acceptor for the electron transport chain for metabolism, for aerobic metabolism. So therefore, because these cells are using up so much oxygen, we're going to have a low partial pressure of oxygen. So keep that in mind. In our alveoli, we have a high partial pressure of oxygen. Down here, we have a low partial pressure of oxygen. Now we know we're going to have hemoglobin. And we know what the goal of the hemoglobin is. The hemoglobin wants to bind oxygen molecules. So it wants to bind and store a lot of oxygen molecules. Now it wants to deliver and transport that oxygen to the tissues and release that oxygen. That's what the hemoglobin wants to do. The hemoglobin wants to bind oxygen tightly up here. Then it wants to transport and deliver that oxygen down here. So how does the hemoglobin do this? Well, essentially, what happens is once the hemoglobin is up here, essentially 95% of the hemoglobin molecules bind oxygen. And we know that because at a partial pressure of 100 millimeters of mercury, 90% of the hemoglobin binds oxygen. And we can see that in our graph. At this partial pressure of oxygen, we see 95% is bounded. So up here, 95% of the hemoglobin is binding oxygen. So that's good. They're binding oxygen very tightly and they're storing a lot of oxygen. Now that hemoglobin travels down here, and when it travels down here, now only 70% of the hemoglobin is bound at oxygen. And we know that because the partial pressure of oxygen is weaker. And we see at a partial pressure of 40 millimeters of mercury, only around 70% is bounded. So now only 70% of the hemoglobin is bounded to oxygen. So remember, the hemoglobin up here, 95% bounded to oxygen. Once they travel down here, now only 70% of them is bounded to oxygen. So what does that mean? That means 25% of them aren't binding oxygen anymore. And this is simple. If 95% is bounding oxygen here, and down here only 70% is binding, so that means 25% aren't binding oxygen anymore. So that means 25% of them are releasing their oxygen. They're dumping their oxygen for the tissues. So that's good. That's good. We want the hemoglobin to bind oxygen tightly here, and once it travels down here, we want it to release that oxygen. We want less percentage of them binding so they can release that oxygen so the tissues get that oxygen. So that's good. And the point is, up here, the hemoglobin binds tightly. Down here, the hemoglobin binds weakly. And we wouldn't want, for example, what if the hemoglobin bind tightly here, but once they travel down here, now they're still binding oxygen tightly? Well, that would be dumb. We don't want them to bind tightly here. We want them to release that oxygen so the cells can get the oxygen. So we do that by changing the partial pressure. Because the partial pressure is different, now because the partial pressure is lower here, less percentage of the hemoglobin will bind oxygen, so now they can release that oxygen. But not just that, we can go a step further. Essentially what's going on is in this environment, down here in the respiring tissues, creates a very specific environment. The environment here has a high concentration of carbon dioxide. And we know that. We know the Krebs cycle metabolism is releasing a lot of carbon dioxide molecules, so we have a large concentration of carbon dioxide here. And that carbon dioxide is going to react with carbonic anhydrase to create carbonic acid, so we're going to have an acidic environment, acidic conditions down here. And not just that, we also know we have a low oxygen concentration because all that oxygen is being used up. So we have a very specific environment, conditions down here. So these conditions of high carbon dioxide, high acidity, and low oxygen makes the hemoglobin go through a conformational change. So the hemoglobin goes through a conformational change into the T state. And when it's in the T state, it binds oxygen weakly. It binds even more weakly. And if we want to find the oxygen hemoglobin binding curve, for the T state, it would look like this. So we see the T state has a lower binding percentage. For at any given partial pressure, we see it's binding weakly. A less percentage of it is bounded. So essentially the point is when the hemoglobin is down here, it converts to the T state where it binds oxygen very weakly. However, once the hemoglobin travels up here, we have a different environment. We have a different environment with different conditions. We have lower carbon dioxide, so therefore less acidic conditions, and we have a higher oxygen concentration. And we saw with that high oxygen concentration, because of cooperativity, it increases in its affinity. So these conditions make the hemoglobin go through another conformational change into the R state, where it binds oxygen very tightly. So this is good. This is a beautiful system because when the hemoglobin is up here, it binds oxygen very tightly. It turns to the R state where it binds oxygen very tightly. However, when the hemoglobin is down here, it turns into the T state where it binds oxygen very weakly. So therefore, when the hemoglobin is up here, because it's in the R state, essentially it's in the R state, and we see for the R state, we see at this partial pressure nearly 99% of the hemoglobin is bounded. So when the hemoglobin is up here, it binds oxygen very tightly, where nearly 99% of the hemoglobin is binding oxygen. However, when the hemoglobin travels down here under these conditions, it turns to the T state, where it binds oxygen very weakly, where only about 45% of the hemoglobin is bounded oxygen. And we see for the T state, at 40 millimeters of mercury, we see around only 45% is bounded. So the point is, the hemoglobin up here binds oxygen very tightly. Around 99% of the hemoglobin is bounded oxygen. However, when the hemoglobin is down here under these conditions, it binds oxygen very weakly, where only 45% is bounded because it turns to the T state, so it binds oxygen weakly, so only 45% is bounded. So what does that mean? That means if 99% of the hemoglobin is bounded here, but once it travels down here, only 45% of the hemoglobin is bounded. That means 54% of the hemoglobin isn't binding oxygen anymore. So 54% of the hemoglobin is releasing its oxygen. So this is beautiful. This is an incredible system. Where up here, it binds oxygen very tightly, so it stores a lot of oxygen. Then when it travels down here, now it binds oxygen very weakly, so it releases a lot of oxygen. So this is the most efficient system to essentially transport oxygen. It binds a lot of oxygen, then transports that oxygen, now it releases that oxygen. So this is a very efficient system to take oxygen and deliver it to our tissues.